All right, question 3. Now, this was a question about controlling stereochemistry, which means, in the context of the topics we've talked about, it's a question about the SN2 reaction. There is no controlling stereochemistry from an SN1 reaction. So if you find yourself with cations or SN1 written anywhere in your answer, you are completely lost. That's not the point. The point is stereo control is only possible from the SN2 reaction. The SN2 reaction is stereospecific, which means 1 enantiomer in produces 1 enantiomer out. The end. No mixtures. That was an important part of this question, which some of you ignored. Fine. Don't do it again. You will see this topic again on the final. Fool me once, blah, blah, blah. Okay, so how do we deal with it? We have 2 different possibilities here. The SN2 reaction is always an inversion, period. There are no exceptions. That's how it works. Let me step that back. There are exceptions based on assigning priorities, but the SN2 reaction is always a stereospecific attack opposite the leaving group. So, in a case where I see something that looks like I've kept the stereochemistry, the product on the left, it means I've had to flip it twice. I don't get to keep it. It has to flip. So if I see something where my nucleophile is in the same stereochemical spot as what would have to end up as my leaving group, it means it's gone through 2 inversions. The other case, it hasn't. It's only had to flip once. That's a straight up SN2 reaction. The question is whether making the leaving group causes an inversion. So, first case, do the right one first, it's simpler. We make a sulfonate. Commonly, this would be something like a toluene sulfonate, but we could use a mesylate, we could use a triflate, there are other options. That gives me a leaving group. The alcohol by itself is a terrible leaving group. But if we make it into a sulfonate ester, then it's willing to be a leaving group. I have not touched this yet. I haven't touched this bond. The sulfonate is just replacing that hydrogen. So it means I haven't changed the stereochemistry by making the leaving group. So that when I bring a nucleophile in, that's the only inversion that happens. So that's how I get the inversion that I see on the right. Retention on the left is a lot more tricky. Still fairly common, but it's a lot more tricky conceptually. Because there is no such thing as retaining it. It has to be inverted. The only way to get back in the same direction is basically to do the equivalent, if you were in a car, of doing 2 U-turns. One U-turn gives you the opposite direction on the street. Second U-turn, you're going back the same way you started. That's what has to happen here. There's no case where the reaction doesn't involve a turn. That's impossible. So, first case, we can do this with chlorine, better off doing it with bromine, so phosphorus tribromide. That is an SN2 reaction. Making the bromide is an SN2 reaction, which means making the bromide inverts the center. So making the bromide gives me this, with the opposite 3-dimensional arrangement to where I started. Then I treat it with a nucleophile, which is also an SN2 reaction. So in the one case, my leaving group does not affect the stereochemistry, that's on the right, so that I have only 1 inversion. In the other case, making the leaving group creates an inversion, and then I invert it again with the nucleophile. No mixture anywhere here. Complete control. If I started out with a chiral alcohol and I'm careful with my conditions, I'm going to get 100% chiral product of one case with the nucleophile away from me on the right, or 100% of it with the nucleophile towards me on the left, without any crossover whatsoever. These are completely different and separate pathways.